Please.
What we have here is a Type T thermocouple. These blue wires on the end are copper, and the red wire in the middle is constantan. And the wires are twisted together at these two junctions, so we have copper constantan, and when the two junctions are at different temperatures, we see a difference in potential, or we see a voltage generated at the ends of the copper wires. So let's see if we can observe that now by clipping our thermocouple, the ends of the copper wire, to our multimeter. And if we turn the multimeter on, we see a voltage of 0 millivolts. That's because both the ends of the thermocouple are at the same temperature. So what we have to do is put one end in a reference temperature. And for that, we will use this ice bath here. Now, ice is at a constant temperature of 0 degrees centigrade, so this is a good reference for us. And if we look at the multimeter, we see that a voltage of 0.5 millivolts is generated. So we see some difference in temperature between the ice water and the room temperature end. And if we want to measure this cup of hot water, we simply stick the free measuring end of our thermocouple in the hot water, and we see that a bigger potential difference is generated, this time of about 1.6 millivolts. And you can look online at the calibration tables that are published for Type T thermocouples to convert this measurement into temperature. And in lab we'll do something just a little bit different. Because the measurements are so small, they're on the scale of 1 or 2 millivolts, we'll be using an amplifier to get a better measurement resolution. Now we're looking at our open air thermistor. It comes in this little plastic container here. And so if we open it up, we'll see right here we have our open air thermistor. We have two lead wires, and then the black thing in the middle is actually our thermistor. And this will change resistance as temperature changes. And the other thing in our container is this piece of paper, and if we flip it over, we see that it has a resistance versus temperature table, at all the calibration that we need. So we can look up, if we measure resistance, we can see what temperature that corresponds to for this specific instrument. So now let's take a look at operating our thermistor. So because we know our multimeter can measure resistance, we'll just hook it up directly to the multimeter using the alligator clips. And we want to make sure that we're set to ohms or resistance. Turn our multimeter on and look for the resistance reading. And we see that this, right now the thermistor is at about 11 kiloohms. If I just simply put my fingers on the thermistor, you can see the resistance starts changing, indicating that the temperature is changing. And you can look up in the calibration tables to see what temperature this corresponds to. So here we have our thermistor set up in a voltage divider. And we do this because thermistors change resistance with temperature. But since resistance is a physical property, most data acquisition devices don't actually measure resistance. So we have to put the resistance in terms of something like voltage. And to do that, we use our voltage divider. And drawing up what a voltage divider looks like conceptually, we start with a voltage source up here, and we come into a resistor, which we know, and that's known as RA. And we go into our unknown resistor, which is what we want to measure, known as RB. And then out of that resistor, we go back to the negative of the power supply. And now to actually measure what our resistance is, we need to come along and measure the resistance, or the voltage, excuse me, across the resistor. So what we have here set up in the background is an actual voltage divider circuit. So if we keep in mind this diagram we have here, this being our source voltage, we have our source voltage starting here, and if we follow the circuit, we come into our known resistor RA, which is provided by a resistance substitution box. And in this case, we've set it to 10 kiloohms. and that is between the two green posts. And then next in the circuit we have our open air thermistor here, and that then is connected back to our power supply. And so that's this portion of the circuit. And now to measure the voltage across the resistor, we come in with our multimeter and we measure between the two ends of the resistor right here. Right now we should get 0 volts because I haven't turned on the power supply yet. And our power supply is connected to the constant 5 volts, and we see here that we get a voltage of about 2.609 volts. And we can use Ohm's law and the voltage divider equation to figure out what the resistance of RB is. So in our voltage divider circuit, we've replaced our open air thermistor with this immersion thermistor, which has a metal sheath around the thermistor to keep water from getting in to the resistor and changing some of the physical properties of it. It works in the exact same principle, however, and so again, if I just measure the voltage across the thermistor, we see a voltage right there that corresponds to the temperature in the room right now. And so in lab, you'll be using the immersion thermistor to measure the temperature of various liquids, such as this heated water here, and you can see the voltage is changing in response to the resistance of the thermistor changing, and that's governed by the voltage divider law, and ice water. And we can see that the voltage is changing now in the opposite direction. Alternatively, we can also use a data acquisition to plug into our voltage divider circuit and measure time varying temperatures such as hot water cooling or ice water warming. Is put one end in a reference temperature, and for that we use an ice bath, which is a temperature of 0 degrees Celsius, which is a good reference to have.
It was so good.